The first thing we are discussing is Cartesian coordinates. So let's start by looking at a 2D Cartesian plane. So I'm going to be using this one, which is the XY plane. And we know this because, as you can see down here from this indicator, our x-axis is horizontal and our y-axis is going to be this vertical line here. So any point on this plane can be represented by its x and y coordinates, and these will always be relative to your origin, which is this center point here. So it's 0, 0, 0 on your x and 0 on your y. So for example, let's take a look at this point here. All right, so we can represent this point by using its x coordinate, which we can see it's displaced 2 on the x-axis, and then 1, 2, 3 on the y-axis. So we can call this point 2, 3. All right, and we can actually, if we select this point and look over here, we can see that. So Maya can tell us the exact translation on the x and y axis. So again, 2 on the x, 3 on the y. And notice here we have our third axis, or z-axis, which is at 0. Now, obviously, if we were looking at this in a 3D plane, so I can go back and have a look here in our 3D view, where we can see that we are over 2 on our x. Here, our y is up here. We can't actually see it, but we can see that it is up on the y-axis. And we can see clearly too that our z-axis, which is our third axis, along here, is still at 0. And so no matter where we plot points on this xy axis, our z-axis is always going to be 0. So for that reason, we don't need to write it down. So it could be 2, 3, and we could add our third coordinate, or 0 here. But because we are only working in our 2D plane, we just assume that our z coordinate is 0. Now that we have our point, let's have a look at some more points. So again, this is in our positive 2 and positive 3, but we can also have this point here, minus 4, 1, or let's say we had another point, minus 2, 2. So again, all of these, for the minus 2, 2, you are moving minus 2 on your x-axis and plus 2 on the y, and that's how you're defining your point. Now that we have our coordinates, we can use these to create vectors. So a vector is defined by its magnitude and direction. So let's take a look at the vector between these 2 points here. So we are going to make the bottom point here, minus 4, minus 1, the tail. And we're going to define the top point here, minus 2, 2, as the head. So we'll look at that vector there. We can denote the vector then from the translation of the tail coordinate to the head coordinate. So in this instance, we would say that our vector, our first coordinate in the vector would be the x coordinate in the head minus the x coordinate in the tail. And our y coordinate will be the y coordinate in the head minus the y coordinate in the tail. So I'm just going to pop up the script editor here, and we can take a wee look at that. So again, our head point coordinate is minus 2, 2. Our tail, we know it's minus 4, minus 1. So then for our vector, again, it's going to be our x coordinate in the head minus the x coordinate in the tail, and the y coordinate in the head minus the y coordinate in the tail. So I'm just going to run this. Okay, and then let's have a look and see what v is. We can see that the resulting vector here is 2, 3. Perfect. So that means that we can define this vector as 2, 3. We are going to rename this, so I'll just remove this annotation and remove this one, and we are going to on our head here, we're just going to give it a new name, and this is going to be 2, 3. So this is our vector v. We'll just go 2, 3. All right. If we create another vector from the origin to the coordinate 2, 3, we can also see that this vector can be defined as 2, 3. So that's our x coordinate in the head, which is 2, minus the x coordinate at our tail, which is the origin, so minus 0. And the same with the y coordinate, 3, minus 0. So So that means that this vector is also defined by 2, 3. So here we have two vectors that we have defined by 2, 3, but we can see that they're in different positions within our xy plane. But because our vectors are defined by magnitude and direction, although they're in a different position, we can formally say that these two vectors are the same. And if we want to even move this vector, we can see that if we put its tail at the origin as well, that it fits in exactly with the vector underneath. And again, this is showing that they are the same. And because of this, it's common practice to display all vectors with the tail at the origin. This is just for ease of calculations and for clarity. It's much easier for us to see than if we have two vectors, if they are the same, when they're all starting at the origin. So going forward, I will be using the origin as the tail for all of my vectors. Okay, so now that we've defined our vectors, we're going to look at vector addition. So we have our vector A here, 2, 3, and I'm introducing a second vector B, minus 5, 1. Okay, and we're going to look at adding these two. So we'll start with adding A plus B. And when you add two vectors, your result is also a vector. So again, our resulting vector here should be A plus B. So we'll start with our A, the first part of it. So we know we're starting at the tail of A and we're moving to the head of A. And then what we're going to want to do is add the B vector from here. So because direction is important again, we're going to be looking at moving the tail of B to here and continuing on to the head of B. And then our final vector will start at the tail of A and end at the head of B. So I'm just going to take vector B here and we're going to copy it. And then let's move this one up so we can see what we're talking about. So I have moved the tail of B onto the head of A. So again, we're going up A and then plus B. So this is going to be our final point. Tail will remain the same, the origin here, and this is going to be the head of our new vector. I'm just going to call this vector C. So there we go, minus 3, 4. And while we're here and we have these vectors, we can actually really easily show that addition is commutative. So there we had A plus B, and now we can show that B plus A will give us the same vector. So again, we're starting with B in this case. So we're going to start at the tail of B and work our way to the head. And then plus A, so we're going to want to take our vector A here. I'm going to copy it and we're going to physically move it so we can really see what's going on. So we're going to pop the tail of A onto the head of B, and you can see that again, we end up right back at this point. So whether we go A plus B or B plus A, we're going to end up with this vector C. Now that was pretty clear, so let's look at the maths behind that, shall we? So I'm going to pull up my script editor. So we have our two starting vectors, A and B, so let's run that. And then, so C1 here. So again, this is our vector C, which is A plus B. So we have our first coordinate in A plus our first coordinate in B, and then the second coordinate in A plus the second coordinate in B. And if I run that, and then we have a look at C, we can see that it's minus 3, 4, which is exactly what we got when we graphed it. And then we can have a look at the second one, which is B plus A. Run that. So again, we've used the same formula. And we'll have a look at C2, and we can see there again that it is minus 3, 4. So whether you do B plus A or A plus B, you're going to end up the same. So next we can look at subtraction. Now this isn't commutative, and that'll be pretty clear when we go through the two examples. So let's start with A minus B. So again, we have our A vector here, and we're going to take our B and we're going to move it. But now this time we're minusing B. So we're starting at the tail of A and ending at the head of A. That's still positive, so we want to go in the same direction. But we're actually going to move the head of b here, because we're going to minus b, so we're going to go the opposite way with our b. So again, instead of adding b and heading over to this point here, we're going to take away b, so it's going to bring us out here. And we can call this point, b, and again, it's a vector that we get the result of, and this is our vector d. So this vector is a minus b. And now we can have a look at b minus a, and it'll be pretty clear that it is not the same as a minus b. So our b is positive, so we're going to go up to b, and again, we're going to copy our a vector here, and we're going to move it. And again, if we were adding this, we'd be adding the tail of the vector to the head of b, and we know that that brings us up to c, but we're minusing a, so we're going to be going in the opposite direction than a, so I'm going to put the head of a here, and head down to the tail. And let's call this vector vector e. There we go. So once again, very clear that these are two different vectors and not commutative. And let's have a look at that in the script editor as well. So for d, we have the first component in a minus the first component in b, and then the second component in a minus the second component in b. And for e, again, we're doing the opposite. So it's our first component in b minus the first component in a, and then second component in b minus the second component in a. And I'm just going to run both of these. And then again, if we have a look, we can see d is 7, 2. Yes, that's what we have here. And we'll look at our e vector, and this is minus 7, minus 2. And that is vector addition and subtraction. Now we're going to look at the unit vector. We're going to use this vector here, vector v, which is 4, 3, as our example. So our unit vector is always going to be of length 1. And that's the important thing to remember. And the process of transforming a vector into a unit vector is called normalizing. So we are going to normalize vector v to create our unit vector. And the unit vector will be in the same direction as v, but its magnitude is going to be 1. And the main reason we do this is for simplifying calculations. That's kind of the main reason they exist. In order to normalize this vector, what we're going to do is we're going to divide each component by the magnitude, by the length of the vector. Now we're going to be looking into getting the magnitude or length of the vector shortly. So we won't go into the details of that just yet. But again, the main point and the main process of normalizing a vector is dividing by the magnitude. So I'm going to pull up my script editor here. So we have our vector v. So we're going to run that. I'm just going to import some math to be able to use the square root function here. So again, we're going to get the magnitude of vector v. So this is the square root of our first component squared plus our second component squared. And again, we're going to be looking into this in more detail in the next section, but we're just going to run that, and then let's have a look and see what our magnitude is. Okay, so the length is 5. So the length here of this vector we now know is 5. So to get our unit vector, it's going to be, our unit vector is going to equal 4 divided by 5, and our second component is going to be 3 divided by 5. And we can just have a look at that here. All right, so now we have our unit vector, and as you can see, the direction is exactly the same, but this length here is going to be 1. All right, so we saw a little bit of it when we were getting the unit vector, but we're going to look at it in more detail now, and that is how to get the length of a vector. So this is the length or the magnitude. So first thing I'm going to point out is that we can actually, using this line, we can make a right angle triangle. So we know that we're going across 4 units, and we know that we're going up 3. So if we use these points, we can see, so we're again across 4 units and up 3, and we have a right angle triangle here. And now that we know that, we can actually use Pythagoras' theorem to help us get the length of the vector. So just for a wee reminder here, we have our 90-degree angle here, and we have side A, which for us is 4, our B would be 3, and then C, which is the hypotenuse, is the length of our vector, and that's what we're looking for. So this says that C squared equals A squared plus B squared. So then if we want to find C on its own, we're just going to get the square root of both of these. And I can pull up our script editor here, and we can see that that is what we were doing. So once again, we have our vector V, and I'm just going to import these maths functions. So the magnitude of V, or the length of V, is going to be the square root of V0 times V0. So our first component in V, which is our 4, which is our length 4 here, so we're squaring that, plus V1 times V1, which is our second component in V here, our 3, and we know that that's our length here. So we're going to get the square root of 4 squared plus 3 squared, which should be the square root of 16 plus 9, which should be the square root of 25, which should be 5. And if I have a look here again, yep, our result is 5. So that tells us that the length or magnitude of our vector V is 5. Next, we're going to be looking at multiplying vectors. So there are 2 different ways of doing this. So there's the dot product and there's the cross product. So first we're going to be looking at the dot product. We use the dot product in order to calculate the angle between 2 vectors. So we're going to have a look at that now using these 2 vectors that I've created. So we have vector A, which is 4, 1, minus 1. And we have our third components here because we are in our 3 dimensions. And then our second vector B, which is 2, 3, 1. All right, so firstly, we'll look at getting the dot product. So that would be denoted as A dot B. And I'll pull up my script editor here and we can have a wee look. So we'll just run those to have again our vector A and our vector B. Now, our dot product. We can get the dot product, so that's A dot B, by multiplying the corresponding components for each vector. So we have the first component in A times the first component in B, and we're going to add that to the second component in A, to the second component in B, and we're going to multiply our third components as well and add those on too. So I have run that and we'll have a wee look and see what we get. 10. Okay, so our A dot B here equals 10. And note that our result here is not a vector. Unlike our previous calculations where our result returned a vector, with the dot product, we get a scalar. Okay, so now that we have A dot B, we can use that to find this angle, and we can do that by using the cosine rule. So if I just move down here, we can see our cosine rule will give us that A dot B equals the magnitude of A times the magnitude of B times the cosine of our angle. So I've just called our angle X here, and we're going to try solve this for X. So before we do that, I just have our magnitude of A and our magnitude of B. So I'm just going to run those so we can get those values. And then if we can use this, formula and rearrange it, find out what X is. So X is going to be the inverse cosine of your A dot B divided by your magnitude of A times your magnitude of B. And this function here actually returns result in radians. So I've just gone ahead and used the degrees function here. So it'll change all of this to degrees. So let me run that there. And then let's check X. So X is 50.95, so almost 51 degrees. So again, that means using the dot product, we've been able to figure out that the angle between these two vectors is 50.9 degrees.
Now we're going to take a look at the other way that we can multiply vectors, and that is using the cross product. So what the cross product can do for us is get a resulting vector that is perpendicular to these two vectors. So the cross product for A and B is going to be it's going to result in a new vector that is going to be orthogonal or perpendicular to A and B. So we can create a plane here between A and B, and our resulting vector is going to be perpendicular to this plane, and the tail will also be at the origin. So let's look at how we do the calculations. So I'm going to pull up my script editor, and for the purposes of the calculations, I am going to call the first bit in A, the first component in A, A1, and then A2, A3 for the second and third, and the same with B. So to get our first component in our resulting vector, we're going to multiply A2 by B3 minus A3 by B2. For the second part, we're going to multiply A1 by B3 minus A3 by B1, and all of this is going to be multiplied by minus 1 for this second component. And for the third component, we get this by multiplying A1 by B2 and minusing A2 by B1. So now let's run this, and we'll have a look at T, and we can see that our resulting vector is 4, minus 6, and 10. Okay, so let's have a look at that on the graph. So this is our vector T, here it is. And yes, so this is perpendicular to our to A and B, our vectors A and B, and that is the cross product. So now that we have a better understanding of vectors and how we can use them, we can discuss their importance in computer graphics. So obviously, if we consider especially things like animation, you know, there's always going to be a lot of movement. And what vectors allow us to do is take things like force, velocity, weight, acceleration, you know, displacement, all of these kind of things, and they help us visualize them and calculate them also, you know. So really, if you're thinking of any sort of movement in the real world, if you want to put that into your scene or in 3D, vectors are really going to help you to translate that into your scene. And if we come back into Maya here, again, we're working in a 3D space. It's very easy for us to visualize vectors as we did in our previous examples. And I'm just going to take a quick look at this cube here to just show how Maya uses vectors itself. So I just created this cube, and we can go up here, we can see I haven't translated it or moved it at all on any of the axes, and we just have it scaled to 1 on each axis. So I can take a look here, and I can look at the vertex. So we can see that each point is a separate vertex. And really what Maya has done is created vectors from the origin to these points. And it uses the knowledge of vectors to translate these for us. So, for example, let's say I wanted to scale 2. Now I'm only scaling on the x, right? So if we do that, we can see that it's come out here and here. And notice that it does it both sides. And that is because, again, if you're imagining the origin at the center, and we want to scale our x coordinates, that means that our x coordinates for all of these are going to go out 2, and the same for here. So these would have already been minus, And you're doubling those, so they're going to move out too. And if we think of that versus the translation, so if I was to translate this 1 on the x, you can see it's moved this way, but it's moved everything. So we've +1 our x coordinates for each of these points, and it's moved the blocks.
And this is just a simple example of how vectors are used in computer graphics.